Dr. Abhnil Prasad from University of New South Wales. He's a researcher at Climate Change Research Center, University of New South Wales, Australia. And he has agreed to talk about introducing you to the basics of radiation. Abhnil, over to you.
Thanks, Vishal. Thanks to the organizing committee for inviting me to this program. I'm really honored. A bit unfortunate not to make there in person, but I think I would try to cover most of the basics of radiation, which would be, I think, quite beneficial to students who are out there and also researchers, I think, who have joined the program as well. So, as Vishal has introduced me, I'm a researcher in University of New South Wales. I do quite a bit of work in climate physics. I also work in applied climate sciences as well. So, more of an interdisciplinary researcher. Today I will just focus on radiation. I should I think acknowledge that I have taken some of the slides of lectures presented by Professor Jason Evans here at UNSW, so credits to him as well. But I've tried to add in a few extra things just to make it in line with the program for today. So let's start. Okay, so I'd start with the defining some of the energy concepts. So energy, as you know, is the main driver for all human beings and all the other instances of processes that happen in the atmosphere as well. So to start off with, I'd suggest that most importantly, we have the potential energy stored in a system. So for example, here we have rain droplets falling on the surface. So from a height, when it falls, it starts gaining speed, and that's how potential energy changes to kinetic energy. Now, kinetic energy is basically due to motion. As you can see from here, the polar jets are the movement over the poles, and the subtropical jets are examples of or possesses kinetic energy. Another concept that is quite important for radiative, even for radiative transfer, is the conservation of energy. So, for example, in a closed system, we have energy conservation. So it's neither created nor destroyed. For example, here we have a vehicle being ascended from a height, and you can see that as it comes down, the kinetic energy increases and the potential energy goes down, whereas the total energy stays the same. So this concept would be used in understanding the basics of even climate models. And I would come back to that later as well. Now, in terms of energy transfer, the transfer of energy in the atmosphere occurs through the transfer of heat. And there are three primary transfer processes. Conduction is one of those, which includes collisions at a molecular level. Then we have convection, which is through movement of fluids. And in atmospheric sciences, you'll also hear a lot about convection. How energy is transferred in the atmosphere through convection is also quite important. But then we have radiation. Radiation is the transfer via the photons. So in this image, as you can see, you have the sun, which hits the ground. So at the surface, depending on the type of surface, whether it's ocean or land, you will have some sort of conduction, which is where the land surface will heat up and it will interact with the upper or the boundary layer in the atmosphere, and that happens through conduction. And as air parcels rise, you can see warm air would rise, and that would lead to convection. So in a nutshell, energy transfer occurs through these three major processes. Now, I will mostly cover radiation, but later on, you'll also hear a lot about convection as well. So let's come to radiation mechanisms. So there are various mechanisms through which radiation interacts in the atmosphere. So, for example, in this image, you can see you have incoming solar radiation at the top of the atmosphere, and you can have absorption at the surface, as I told you before, which is basically energy that is retained by the surface. So photons will interact with the surface and some of it would be absorbed. Well, there'll be some which will be reflected as well. So this is the portion that goes back into the atmosphere. And that really depends on the type of surface as well. I'll be talking about albedo also, which is basically which defines how much of the energy is reflected back into the atmosphere. Then there is the mechanism of scattering. This is where we have electromagnetic waves which change from propagating in one direction to all directions, and that is shown here. So for example, you have photons interacting with aerosol particles. They will scatter the photons in different directions, and that also would give rise to diffuse radiation. That's something, diffuse radiation is also quite important because it adds to the net radiation reaching at the surface. Now, there's also refraction depending on the type of material. For example, in water, you have some sort of propagation of EM waves which change direction based on the density of the material. And then you have transmitted energy, which is basically as photons passes through the atmosphere, you have some sort of transmissivity in the atmosphere. So you have rays passing through the surfaces. If it's opaque, then it becomes quite difficult for transmission to occur. But after absorption, the energy that comes out is basically the transmitted energy that goes and hits the surface at the bottom. Coming to electromagnetic waves, this figure shows basically how the electromagnetic waves propagates. You can see you have the magnetic field and the electric field in parallel to each other. You have the speed defined as lambda times the frequency. So you can see the lambda is the wavelength of the wave. That's the distance between the two successive crusts as shown here. And the speed is basically calculated in meters per second. When you compare the energy that is transported, you have the energy given as h times v. H is the Planck's constant and v is the velocity. These two expressions here are quite important because it would be used later in understanding the basics of radiative transfer. Now, Planck's constant here is derived using the famous photoelectric effect, which was done in the early 1900s to discover this constant. We'll move to the electromagnetic spectrum. So how is radiation treated? You can see it's defined, or it's basically split into different wavelengths or frequencies. And you can see you have all the way going from radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays, and they all are defined by either the wavelength or the frequency. Now whatever we see is in the visible spectrum here. So that is what is visible to the eye, but the other frequencies are not visible to the eye. But obviously they have applications, and there's various applications that I talk about later on. The famous one is X-rays. Everyone here would have probably heard about it. In medical sciences, is widely used to understand for example, if there are issues with bones, or if there's a breakage in bone that easily shows up in an X-ray image. In the atmosphere itself, if I break it down again, you can see the atmospheric opacity based on different wavelengths. So you can see here, this is now the gamma rays here. It's basically blocked by the upper atmosphere. So you can see there's a lot of absorption. And then if you come, this is where the visible light sits in. So this is at around one micrometers here. And this is again observable from Earth. And it has some atmospheric distortion as well. And then we have the infrared spectrum, which sits over here. You can see all of them have different absorption, especially in the atmosphere. They behave differently. And I'd be using this later on in demonstrating how the atmospheric window technique is used by satellites to uh, uh, basically observe the Earth from the space. The definition of spectrum is also quite important. So the curve here is basically known as the spectrum, and it's basically could be of monochromatic intensity. And we calculate the flux density, which is f lambda here, which is on the y-axis, is basically a function of the wavelength. And the shaded area here represents the intensity or the flux density of radiation within the various wavelength range. So next, I'll basically introduce some of the laws that are widely used in radiation physics. The most basic one is the inverse square law. So this is, for example, here shown in the image. If we have the source of emitting radiation S here in the center at a single wavelength, which is basically from a monochromatic source, we can calculate the total flux area over the area conserved as the we can see, which is here given as FR times 4 pi r squared, because we have the area surface area, which is the area with which it interacts is 4 times the area of a circle. And then what you have here is like at that point, you have the intensity defined as 1, but as you go further away, you can see the flux, it sort of behaves or interacts as the inverse square law. So you can see at this point, you have energy, the energy is twice as far away from the source, and it spreads over 4 times, for example, here 4 times the area which it initially starts with. So you can see that flux reduces as the second power of the distance from the source. And this law is quite important, because if we know the intensity of energy emitted from, let's say, one planet, and if we know the distance to the other planet, then we could, in principle, approximate what the intensity would be for the other planet. Moving on to the concepts of black body radiation. So the sun here shown here is a perfect black body because it's perfectly black, opaque object and at a fixed temperature. So it basically absorbs all the incident radiation and does not reflect any radiation. So everything is absorbed and then later emitted. This is the spectrum. You can see the emitting temperature is at around 5,780 Kelvin, and you can see at various wavelength what the radiation intensity is. So, for example, you have 7% of the emitted radiation is ultraviolet. Then you have 44% that sits in the visible spectrum, and then you have the 37% in the near infrared, and then the less than 1% is basically the larger wavelengths. So the spectral radiance that you show here, that is shown here, the curve, the way we derive that is basically using Planck's law. That is, the spectral radiance of a perfect black body is basically described by the Planck's law, which is given here. You can see it's a function of lambda and t, and we have the Boltzmann's constant here, which is kb in this expression, and this expression can be used to basically look at the spectral radiance from a black body. Now, as I said before, b lambda has units power per solid angle, because it's basically it will interact with the spherical system, and it also is you can see it's available at per wavelength. And it was one of the earliest triumphs of modern quantum theory in the early 1900s. I will not go into the derivation of this, but it's easily available and it's easily derived using quantum and statistical mechanics. Now, if I go back to the black body curve, you can see at different temperatures how the spectrum would change. You can see this is for the spectrum at 300 Kelvin, and as you go up, you can see the edges of the curve changes drastically. You have a sharp rise at shorter wavelengths, and then you have slower falls at larger wavelengths, and then you have the peak, which sits here in between the rise and the fall of the spectrum. And then anything less than 4 micron would be in the visible, which I would show here. For example, this is if we look at Sun and Earth, there's a perfect black body. You have the emitted temperature of Sun is 5780 Kelvin. For Earth, it's around 255 Kelvin. And then there's this separator, which is at around 4 micrometers. So anything less than 4 micrometers would be in the shortwave spectrum, and anything above 4 micron would be in the long wave spectrum. Now, whatever is emitted in the atmosphere, you have different absorption depending on the constituent. For example, this is at ground level, and this is at 11 kilometers in the atmosphere. So the absorption properties are quite different. For example, here you have water, how water molecules behave at near the ground level and in the atmosphere is slightly different. So it's highly important because the different constituents would all behave differently, and that basically is quite important, because if later on when we use these sorts of concepts to understand radiative transfer, we have to account for the absorption rates of these constituents. Moving on to Wien's displacement law. This again is also quite important and used in the literature. This is the spectral peak. So the lambda max that I was talking about here, and for a black body curve, it is defined as using this formula, which is 1 by x hc over kBt, and this is basically derived by differentiating the spectral function here. So whenever it's 0, the rate of change, we would come up with the Wien's displacement law, which is basically describing how to get the lambda max. It basically tells us that as the temperature of an object increases, the maximum in the spectral irradiance move to a smaller wavelength, which is inversely proportional with T. And it basically is quite useful in telling us the approximate temperature of an object. This is also known as the color temperature. So for example, if you're using a spectroradiometer and you're shooting it to, let's say, a box, what you'd get out from that is basically the color temperature, which reflects the lambda max or the spectral peak in the black body curve. Am I doing the time? Okay, so next is like the other important concept is about Stefan Boltzmann's law. Now, still talking about the black body, you can see that the total energy flux leaving a perfect black body at a temperature T would be given by sigma T to the power 4, where sigma is basically given by this expression, which is basically the Stefan Boltzmann's constant, also widely used in computing the outgoing long wave radiation in the atmosphere. And this is again derived from the Planck's law, basically by integrating over all solid angles and wavelengths. So this is the integration over all the wavelengths and solid angles. So for example, if the flux density F can be measured from a black body or a non-black body, we can estimate the equivalent black body temperature or the effective emission temperature TE using this function. So what about imperfect black bodies? So obviously there's all objects are not perfect black bodies. There's some which are imperfect, and they would obviously deviate from our idealized black body assumptions. But we can measure this deviation through something known as emissivity. So emissivity here is given as you can see the emitted intensity divided by the input, and it's obviously if it's a black body, then this value is close to 1. But if not, then it would change. For example, the emissivity of the Earth's atmosphere would vary substantially due to change in cloud cover, or the concentration of greenhouse gases if T is not uniform. Okay, so moving on, we can also define 3 additional quantities that measure these deviations from perfect black bodies. So you have absorptivity, which is basically the amount that is absorbed compared to the incident. We have the reflectivity, which is the amount which is reflected from compared to the incident, and then the transmissivity, which is again the amount that is the intensity that is transmitted in comparison to the incident. And you can see that if it's a black body, then as I said before, black bodies would be perfectly 1 because it totally absorbs all the intensity. But if and then it for a black body, the reflectivity and transmissivity would be 0 because it doesn't reflect or transmit it. Next, we come to Kirchhoff's law. Now, this is again related to absorptivity. So it basically equals the emissivity at a given wavelength. This basically means that good absorbers are also good emitters. So whatever is absorbed would be emitted, and basically the absorption, the rate at which intensity absorbed or the energy is absorbed would be reflected as well. And Kirchhoff's laws basically can be used to determine the absorptivity and the emissivity for different surfaces. Kirchhoff's law is also an intrinsic property of matter and holds for all cases that can be considered. We do know that the emissivity does not vary with wavelengths for gases, which are found in the Earth's atmosphere, and that is where we start using the Gray approximation, where we say that basically the emissivity for different wavelengths just remains constant. This figure here shows the transmittance spectrum. So this is, you can see at the top is the spectral intensity. Again, the downwelling solar radiation. So this is in the visible. This is what is emitted in the infrared. What you have here is radiation propagates through the atmosphere. So you have the absorption, you have the transmission, and you have the reflectance. So you can see that all this would basically add to 1. But if I come to the major components for the absorption and scattering, so this is when you combine everything, you can see the transmittance is not uniform. So obviously, if it's a black body, then you'd have that basically follow that curve. But because of this total absorption and scattering, which is basically coming from all the major components. So for example, here you have the major components as the water vapor, you have the carbon dioxide, oxygen, ozone, methane, nitrous oxide, and then you have the radar scattering as well. So all these have basically different absorption and scattering at different wavelengths. You can see water vapor is quite dominating here as compared to other constituents. But the important thing here is that you can see that the shortwave spectrum is quite pronounced, and then the long wave spectrum is also it's the emitted radiances sits at that infrared level, and that is something that could be measured from space as well. So moving on to the concept of albedo now, because we're talking about the reflected radiation from the surfaces, and albedo is something which can measure what the fraction of total solar radiation which is reflected from the Earth's surface, and this is again averaged over all solar wavelengths. And the albedos could be quite different for different surfaces, because different surfaces will absorb solar irradiance differently. For example, here you can see this in this figure. You have snow. So you can see it's white. It has high albedo. So most of the incident incoming solar radiation gets reflected. Then you have the forest, where the albedo is around 10 to 20%. So basically, just 20% is basically reflected. And then you have the grass, which is again the shrubs. They all would have different albedos. You can see ocean will also have a different albedo, and all the albedos will basically decide how much energy is absorbed and how much is reflected. So coming to the concept of radiative equilibrium, this is quite important as well. So you can see here in this figure, basically the incoming radiation is balanced by the outgoing radiation. So that's basically radiative equilibrium. You have the total incoming power equal to the total outgoing power. We can assume you can use a billiard board approximation for planets, so we can assume it's basically spherical. So you have the incoming radiation, which is which is affected by the planetary albedo. So we have to apply that correction, and that is the solar constant. The area with which it interacts is just the pi r square, which is the area of the circle here. But the radiation, the emission is it's basically occurs through the whole sphere. So you can see it's emitted in all directions. So you have the area of emission flux, which would be the four times pi r squared, and then you have the sigma t to the power of 4 for the outgoing radiation. Once we put that together, you can see that the incoming solar radiation is balanced by the outgoing long wave radiation, where we define the effective temperature, so at which the which the outgoing long wave is emitted through. And once we rearrange this formula, basically we have the equation for the effective temperature, which is basically governed by the albedo and the solar constant. Now this is again, as I said, is the radiative equilibrium temperature, or the effective temperature, and we can plug in the numbers for albedo. For example, for surface albedo, average would be around 0.3. We have the solar constant, which is 1368 watts per meter square. So this is what is coming at the top of the atmosphere. We put in the radius of the Earth. And substituting all these numbers into the equation, you can get the effective temperature at 255 Kelvin, which is minus 18 degrees Celsius for Earth. And if we use the Wien's law, we could calculate the lambda max at around 11.36 micrometers. But the effective temperature that we calculate here, negative 18 degrees Celsius, is, you can see it's quite cold. So the radiative equilibrium temperature is much lower than the surface temperature, and there's various reasons for that, because in the atmosphere we have many atmospheric gases which are selective absorbers. We have carbon dioxide, water vapor. We have also terrestrial absorption and shortwave absorption. We have the atmospheric window, which allows for long wave radiation to pass through, and all bodies emit and absorb radiation. So atmosphere acts like, for example, acts like a roof of a greenhouse. Sometimes we call it as an atmosphere effect. And then get some sort of realistic surface temperature, we can start using a simple greenhouse model, which is shown here. We can see that this is, for example, this is the atmosphere, this is the surface. The assumptions here is that no solar energy is absorbed by the atmosphere. This is again just a simple approximation. We assume that atmosphere is a perfect long wave absorber. So you have the short wave, and then this is the long wave in green. They can be treated separately. So short wave and long wave can be treated separately. And we can say that atmosphere also emits equally to space and ground. So here you have equal sort of emission in towards the ground and towards the space. So again, we can use the concept of radiative balance for incoming radiation and outgoing radiation. We can consider each layer. So, for example, in the incoming layer, the energy here is equal to that the sigma Ta to the power 4, and then we can also use here. So you can use the ground as a reference to build up the second equation, which is E plus sigma Ta to the power 4 is equal to the sigma Tg to the power 4. So that is at the ground. So now we have two equations. If we have two equations, we can solve the two equations together to get the ground, the temperature at the ground, which should be equal to 1.18 times the temperature of the atmosphere. We can plug in the numbers again with E is calculated this before, 1 minus alpha into the solar constants divided by 4. Using the albedo as 0.3, we can get the effective temperature of the atmosphere as 255 Kelvin, and the ground temperature is 300 Kelvin. And this is a bit closer because you have the global average surface temperature sits at around 288 Kelvin. So you can see that just having the another layer which gives this greenhouse effect, you can see that the Earth's surface temperature would be much colder if without the greenhouse effect. So initially we computed something which was around negative 18 degrees Celsius, but now we're getting more closer to the acceptable range or the measured range of global surface temperature. But this again is just a simple greenhouse model. We can go on further and try build a more realistic greenhouse model so that the effective temperature is more closer or more in agreement to what is observed. So now what we can have is, we can have again the atmosphere and the ground. We have the solar radiation which gets reflected from the ground with the albedo. We have the absorption in the atmosphere, which is given by A here, and the absorption at the surface, which is given by this 1 minus A minus the albedo to the incoming, which is given by E. Next, we can look at the terrestrial radiation. So whatever is now emitted in the infrared, you can see at the atmosphere level, you have this function here, which is E emissivity into sigma into Tg to the power 4, and then you have so that is what is also emitted from here. You can see at the top of the atmosphere, you have 1 minus E into sigma Tg to the power 4th, which is emitted up. So this is this number here. We also check in the happenings in the atmosphere as well. So whatever is happening in the atmosphere, so you can see these two arrows here. You can see that you have emission from both into space and to the ground, which is again given by E sigma to the with the temperature of the atmosphere. So whatever is the temperature here to the power of 4, which is basically emitted to space and ground. So we're having more components to the model. We again apply the radiative balance. You can see that again incoming it should be equal to the outgoing. We look at the three components: what is happening to space, what is happening in the atmosphere, and what is happening at the ground. So you can see in the space, the incoming you have E, and you have all the outgoings here. You have alpha E, you have 1 minus E into sigma T ground to the power 4, and then you have this whatever is emitted from the atmosphere in the long wave as well, which is E sigma TA to the power 4. In the atmospheric layer here, you again have the absorption component, I into E, and then you have E sigma to the power 4, which is now the incoming, and then you have the outgoing, which is the 2 times the sigma ETA to the power 4, which is these two here. And then looking at the ground again, you have these this component here added to this component here, and then you have whatever is outgoing, which is sigma TG to the power 4. So now we have 3 equations, and we have the known numbers for, we can assume the absorption coefficient is 0.1, emissivity is 0.8, the albedo is 0.3, solar constant is 11368, and we can plug these numbers into the equations as before, and what you can get is these 3 equations, which can be easily solved simultaneously. You can see here, once we put in these numbers, we can only use the 2 equations. We can substitute the 3rd equation into the 2nd equation to get the temperature of the atmosphere, which is around 245.7 Kelvin. And then we can also use the equation to get the temperature at ground, which is 284.3 Kelvin. So this is now, you can see, it's a much better global agreement, which is of the order of 288 Kelvin. So that's something that is the global average temperature that is observed roughly. And by including, by making a realistic greenhouse model, we are getting much closer to this value. But there are some model limits. This is just, as I said, this is just a simple greenhouse model with limitations. We still lack a lot of dynamical features. There's no convection, there's no clouds, there's no rotation and circulation, there's no geometry, there's no spatial heterogeneity, there's no learned surface properties. So, but without even adding all these sort of dynamical features, we still get very close to the number that is observed. But obviously, to get to make it more realistic, we have to model these processes as well, so that you have the the dynamical representation of the atmosphere once it's added in, and once the radiative transfer scheme starts acting on that, then you would get a better sort of a picture of how the processes in the atmosphere get resolved. Okay, how am I doing with time? Check.
5 minutes. 5 minutes.
I have just 5 minutes.
Yes.
Okay, so I think I should just move on. Going to Beer's law. So Beer's law basically describes how an energy flux or radiance at a particular wavelength passes through an atmosphere and how it gets attenuated. So you have this incident light coming in, you have the let's say a slab of a layer in the atmosphere, and then the whatever passes out, and obviously it interacts at some angle, it could be a zenith angle, and then what happens is, like, after transmission, whatever is transmitted is basically dependent on the absorption and scattering that occurs in the layer. And this absorption can be proportional to the the absorbing molecule. So density. If I go into the details, you could see that the change in the intensity can be associated with this absorption coefficient, the density of the layer, and the solar zenith angle. That would define the rate of change in the intensity. I'd not go into the details of the maths here, but it's pretty simple. If we integrate on both sides, we can basically derive Beer's law. which is you can see varies exponentially with the optical thickness. Optical thickness is basically this expression here. If you integrate k lambda with rho dz, you'd basically get the optical thickness of the layer. And this it could be clouds, it could be liquid water vapor, and it could be anything in the sphere. We can also define the transmittance based on BS law. So if you know whatever is coming out and whatever is going in, we can basically define that as transmittance. And then the absorptions would be just 1 minus the transmittance. So whatever is absorbed is basically 1 less than the transmittance. We can obviously define the extinction now based on absorption and scattering coefficients, and we can also integrate it all over the wavelengths to get the more clear picture of the extinction for a layer. I'm not going to the details of this, but basically there's the spectral properties of the gases would define the greenhouse effect. And as I think I've talked about this earlier as well, it depends on the absorption and scattering. The greenhouse gases again have different characteristics. The spectral properties are different. So they also absorb upwelling infrared from the space, and after absorption, they can re-emit and thermalize with the surrounding atmosphere. This is an important figure because it shows the radiative forcing in the atmosphere, and there's for different constituents. But you can see here you have aerosols, which give a negative radiative forcing as compared to the other constituents. So these carbon dioxide and other anthropogenic particles, they warm the atmosphere, whereas aerosols and clouds basically cool. And basically this competition between the albedo and greenhouse effect would decide whether you have warming or cooling in the atmosphere. We can use these sorts of concepts to get the radiation budget. So whatever is, as I said before, the conservation of energy holds. Incoming should be equal to the outgoing. So here you have, in this corner, you have the short wave, the incoming solar radiation, how it is absorbed, the proportion which is absorbed, reflected by clouds, by surface is all defined here. And then in this side, you have the infrared radiation. So whatever is absorbed is re-emitted in the long wave spectrum, and you can see the components, how it interacts with the greenhouse gases and the outgoing long wave radiation, which goes to the top of atmosphere. So all these numbers are derived using observations, using satellite observations. And that's what you see here. You have the fluxes. This is the absorbed radiation globally. You can see in the poles, the absorption is much less, so it's also emitting much less. But in the tropics, you have quite high outgoing long wave radiation because you have much higher clouds, much colder temperatures that are emitted. Coming to radiative transfer schemes, there's several complex schemes. On the left, you can see there's the RRTMG, the rapid radiative transfer model. You have the line-by-line radiative transfer models. You have a Motrain, but all of these schemes are built on our simple greenhouse model, but with several other changes. So you have, for example, you have pressure and temperature profiles. You have multiple levels. They're split into wavelengths, bands. They trace gases in the atmosphere. There's microphysics in it as well. You have cloud, rain, snow, other things, and they run inside dynamical models. Probably just this is a radiative transferring action in the WOF model, which is weather research and forecasting model. You can see on the top is the outgoing long wave radiation. So how radiation interacts with clouds and the land surface and the dynamics of the physical system here. You can see that all is computed using the outgoing long wave radiation is basically computed by the radiative transfer scheme, and it's quite important in deciding physical processes. For example, here I was modeling the cloud lines that are observed in northern Australia, and just adding moisture in the column gives a lot of changes to the outgoing long wave radiation. Importance of radiative transfer is also in satellite applications. So you can see the flux can be measured as irradiance, and then using the Planck function, we can get the brightness temperature that is picked up by satellites. In remote sensing, you have, as I said, this figure is similar to what I've shown before. You have the incoming and the outgoing at different wavelengths, and then you have these atmospheric windows. So these are where there's basically not much observation, and we can use these atmospheric windows to actually peer through into the atmosphere at various wavelengths to actually see what's happening from the satellite. You can see these atmospheric windows are here at different sort of locations at different bandwidths. And these bandwidths, for example, for Himawari satellites would be in the visible spectrum, in the near infrared, and in the infrared, and they all are quite sensitive to different physical properties that are seen from the satellite. This imagery basically shows the difference in visible and in the infrared. Again, seeing different, it's basically looking at the atmosphere at different wavelengths. And a nice segue to the other lecture would be radiative convective equilibrium. We all know that Manabe got the Nobel Prize in Physics in 2021 when he looked at radiative convective equilibrium. So I was talking about radiative equilibrium, but once you bring in convection, which is a balance between cooling of the atmosphere by radiation and the heating to the latent heat release at the surface, we get much more clearer picture of how the surface temperature at the of Earth comes into balance when we bring in convection. So in summary, I have just talked about radiation. So this is just one component of the Earth system. There's much more that also affects the physical processes in the atmosphere. So you have the winds, you have the land surface scheme, you have the ocean, the heat transfer between the land and the ocean. You have the topography. So as I say, global climate is driven by radiation, but the Earth's climate is much more complex. And we have several parameterizations which reproduce physical processes in the climate system. And that's all. Thanks for listening. And if we have time, I can take a few questions.
Thank you, Abhi, for sticking to the time. It's exactly 45 minutes. We have plenty of time for questions, around 15 minutes. So I request students to raise hands, and we will probably give you mic sequentially. Maybe I will ask a question from students' perspective. This is a program on moist convective dynamics of monsoons. And the first lecture is on radiation. It's not convection, it's not dynamics. But why do we worry about radiation at all from the student's point of view?
Yeah.
Abhi, do you want to maybe take this opportunity to say a couple
Yes, of course. I think, as I said before, radiation is, so it's basically, we need energy to drive any system. So radiation is that source of energy that gives rise to, let's say, all the dynamics that comes in later on. So example, all the energy that gets absorbed at the surface gets emitted, it interacts with the atmosphere, and that's how all the the physical processes of circulation starts, the processes of let's say cloud formation is also governed by radiation, because if there's no radiation, then there's no heating of the land surface, and then there won't be any ascent of parcels, and all the thermodynamics of the atmosphere would basically not function as it's actually functioning. So I would say that radiation is basically that interface that basically gives rise to all these physical processes. So it's the starting point for all the physical processes, because it's the source of energy which basically starts driving everything. And that would apply to monsoons as well, because obviously in monsoon and monsoonal systems, it's the organization of clouds, and it's obviously it's regional dependent. It really depends where things originate from and where it ends to. And again, whatever happens in the tropics, whatever happens in the poles, the development of the development of the circulations that happens in the atmosphere is all driven by radiation interacting with the physical system.
Thanks, Abhi.
I should say that I haven't really gone into the details of the radiative transfer because I thought this is mostly just introducing radiation to everyone. I think going into the radiative transfer itself is a different animal, and you have to go into the details of the how things interact in different particles interact in the atmosphere using the basic equations, the starting Maxwell's equation, using Maxwell's equation to derive all those interactive happenings in the atmosphere.
Yeah, no, Abhi, I think that was great actually. That gave, I think, a set of reference points for students to explore further, and how a set of thoughts one after the other really motivate the discussion. Thanks. There's a question from one student, please.
So first of all, thank you for your precise lecture about radiation. Myself, Renuka, I'm a research scholar. Actually, I have a small question about effective temperature, as you mentioned in your slides. That is, you shown 255 Kelvin is the effective temperature of Earth without atmosphere. But now, is it exactly we expecting 255 kilometers still?
So I think so. In my slides, I showed different models. So when I start with just a simple model without any greenhouse effect, if you don't have any greenhouse effect, then you get much colder temperatures because there's no warming that comes from the atmosphere. So that's why you have much colder temperatures. But as you add in the atmosphere, you have the absorptions and emissivities of the atmosphere in the model. Then you start having this greenhouse effect, which adds that extra bit of dynamics into the system and gives you a much warmer temperature, which is much closer to what is actually observed in the system. So it's just showing that if you don't have the let's say the atmospheric components, if you don't add in the atmospheric profiles, if you don't add the trace gases, then you get something which you can't explain in terms of the effective temperature at the surface. So that's the whole idea of understanding radiative transfer, is that you have, it's not, if you look at a simple column model, if you just have a column model without an atmosphere, then you get much colder temperatures because there's no atmosphere interacting in the system. And once you start adding the constituents, for example, if you go into more detail, if you start adding, let's say, clouds, which have, obviously different optical depths, they have different albedo and greenhouse effects. So clouds are of different types, they're of different thickness, they are at different heights as well. So they have the emission temperatures are different, the way they transmit is different. So all that, once you start adding in, then you start going to a much realistic, you start getting into more realistic atmosphere, and that's where you start converging slowly to the effective temperature of at the surface. And that's basically what most of our climate models do. Once we start incorporating all these processes, we start getting into a much, we start getting into a close agreement. What I was showing is basically just a segue into, how that process takes place. And as you add in more information, then with radiative transfer and also with other things that happen in the atmosphere, then you start getting a realistic picture of what the surface temperature would be. So does that answer your question?
Yes, sir, I got. Actually, can you give an idea without atmosphere? Okay, anyhow, we know somehow atmosphere is definitely influencing on effective temperature of Earth and all. Then my point is, without considering these greenhouse gases and all whatever, but I want to know how the land surface processes whatever we observed in the previous Earth, and now the Earth surface modifications is so much. We experience more modifications on the land surface aspects, then how these may be, is there any chance these can drive that effective temperature of Earth?
So
Just
yeah,
I
yes, I would say that if you I mean, I don't know if I can share my screen. I mean, show the slides again. But anyways, in the expressions, you would see that we have things like albedo, which is quite important. So any sort of changes to the in the let's say in the land properties would change the albedo, and that the albedo of the surface, and that would directly affect what is happening in the atmosphere. So obviously, of course, if we have changes, and whatever I have shown are basically very static in time. So there's like it's static. If you look at dynamic processes, subtle changes in in the surface albedo, sorry, would affect how the learned surface interacts so with the upper boundary layer, and that would obviously affect the whole column, and then the whole dynamics gets affected, and then dynamically you'll have these changes in surface temperature. So whatever I was showing was just the average surface temperature, so it's just a mean based on some constants. But obviously, in a realistic environment, everything is dynamic. So if you have any subtle changes in the land surface properties, that would directly affect the albedo of the surface, and then the whole processes would get accordingly affected as well. Now, obviously, there are a lot of things happening with land surface schemes. You have the feedbacks that happens, and we have different feedbacks operating in the climate system that would also affect the surface temperature. For example, you have a lot of shallow mixing in the upper boundary layer. You have like dynite sort of contrast as well. You have land breezes, sea breezes. All these sort of processes would start affecting the surface temperature at every model time step, or in realistic time space. So and then accordingly, if you average that out, given how your land surface properties are changing, you would have that would reflect on the surface temperature as well. And again, as I said, I'm just talking about the land surface. You also have to understand that you have the whole atmospheric column, which would interact with the land surface as well. And then this balance between radiation and convection, which would, I think, come in as well, which would decide how the surface temperature of the mean surface temperature, how it sort of changes over time. So I've just touched on radiation. There's a lot of things. I think there's convection, which I think would come in later. There's obviously the dynamics of the atmosphere, which would come in. All these processes would get affected in some way or the other once the land surface properties change.
Thank you, Abhi. So, any other questions? Maybe quick question. We just have a couple of minutes. Maybe if not, let us thank Dr. Abhnil Prasad from UNSW